Last day we have ended with the definition of this binary search tree, where we have seen that there is a very important relationship present between left child parent and its right child, and we can see that relation over here. And also we have seen the idea of uh, subtree. So every tree contain a left subtree and a right subtree, and we have seen this idea, right? So today we will start with the traversal of binary search tree. So BST traversal. So as you know that tree is basically a nonlinear data structure. That means we have seen that in case of nonlinear data structure, the nodes cannot be visited in a single run. Now, what does it mean? I mean, if I consider that I have uh, mm, I have a uh, tree something like this. Forget about, I mean, whether it is VST or not VST doesn't matter. If I consider that I have a tree something like this, and if I print this nodes value in some order, I mean, I'm not interested, we have not discussed yet the what are the possible orders, but still, I mean, if I just arbitrarily write that, say A, then B, then C, then D, and then E, if I write this order, that means we started visiting this node first, and we came here. When you will write program for visiting these nodes, I mean printing these values of the nodes. So definitely one thing is sure that we started from here. This is my root. This is my root. We started from here and we came left first. Then we have printed fine. Now after printing this B, since I have printed C, that means somehow I have reached to this node. Now from B we don't have any path to reach to, I mean from a left child there is no path directly to reach to a right child. To reach to the right child I have to go via A. So that means without visiting a node, some of the nodes of the tree more than once, it is not possible to traverse the whole tree, which is not true in case of a linked list or an array. Because in case of a linked list we have seen that we have a simple connection between the nodes, something like this, a linear connection. So if we have this is this contain A, then this contain B, this contain C, and this contain D, we start from here, this point, without visiting a node more than once, I can easily print ABCD. But that is not true in case of a tree, and here the nonlinearity comes. So that means in which order you are revisiting the nodes depends on that. There are three type of traversal possible in a binary search tree. So the first one we call preorder traversal. The second one we call in order, and third one we call post order. Now see here, this pre, in and post, these three, words are actually a relative word. Pre means before something, post means after something, in means between something. So between which one or after which one or before which, before which one. So let's see this. The order actually, if you consider that we have a node something like, if this is a parent is considered as a node, this is the parent, and its left child considered as L, and right child is considered as R, then the order in case of pre-order will be something like, left, I'm sorry, node N, then left, then R. So that means, uh, first the parent will be visited, then the left child will be visited, then the right child can be visited. So similarly, if you go for in order, it will become the left child will be visited first, then the node, that is the parent, then the right child will be visited first. Visited. And in case of pre-order, the childs are visited first and then its parent. So first the left child, then right child, then the parent, that is n. So you see the position of n with respect to different cases. You see this pre, in, post, these words are considered with respect to the position of this n, because in case of pre-order, parent is before visiting left and right child. In inner, parent is in between left and right child. Post order, parent is in after left and right child. So depends on this the name came. And one more observation is that you see the order between the left and right child has not changed. Left child always visited first and then right child. Okay, so that means if we consider a very simple situation, for example, A is a node and then B in the left side and C in the right side, the pre-order will be A, B, C. Post order, in order will be uh, B, A, C, and post order will be B, C, then A. So, and this is true for every situation. What I mean that we have considered only three nodes, but tree cannot be considered only of three nodes only, right? So, if we enlarge the tree, many for many levels, for each and every subtree, this particular idea is true, recursively true. For example, let's do one thing. Let's first try to create a binary search tree, and then we will see that how we can traverse with different type of order. So if we have, so first we will start with, we will do a BST creation, and then we will do a traverse. So if we have a set of numbers, how we can do that. So let's do one thing. Let's take some arbitrary values over here. Suppose we start with say 10, then 3, then 15, then 12, then 20, then 18, then 5, then 1, and then maybe 6, or maybe uh, 15. Okay, so it will be say 14. Okay, so suppose these are the numbers we have, and we have to create a tree where we have to create a binary search tree. So the left child should be lesser than parent, and parent should be lesser than right child. That relationship has to be maintained. So how we can do that? You see, we always remember, when we create a binary search tree from a set of numbers, the first number always considered as the root. Okay, so we will start with 10 as a root of the binary search tree, because we will start every time for the other values to decide whether it will go towards right or towards left. We will start with 10, start checking with 10. So you see, we have 3 over here, and we will start checking with 10, as we have seen that this is my root of the tree, is going to be my root of the tree. So 3 is lesser than 10, I know. So with respect to the rule of binary search tree, 3 should be in the left hand side of 10. And we can see that left hand side of 10 is still blank. So there is no subtree in the left side of 10. I mean actually left subtree. So since there is no left subtree present, that means I can directly connect 3 with 10. So in the left subtree of 10, now we have only one node, that is 3. Now let's go for 15. Similarly, 15 is greater than 10. So 15 should be in the right side of 10, and we can see still now, till now we have no right subtree of 10. So we can directly connect 15 as a right subtree of 10. That means 15 is the only node in the right subtree of 10. Fine. Now it's come for 12. Now see, 12, always remember, we always check again I'm saying that each and every number we will start checking from this root, and then we will decide where to go. Now when 12 come in the scenario, I see that 12 is greater than 10, so 12 should be in the right side of 10. Now right side of 10 already contain a subtree. Since there is a subtree, we have to move to the right side first, and then with the parent of the right subtree or the root of the right subtree, we can do the checking again. So in the right subtree of 10, we have only one node, and that is the root of the right subtree even. So even when I will go right side once, then I'll find 15. So we will check 12 with 15 now, and we'll see that 12 is lesser than the root of the right subtree. So it's sure that 12 should be in the left side of 15, right? So you see, that means, and left side of 15 is basically blank, there is no left subtree. So I can, without any doubt, I can connect 12 in this side. Fine. Now it's come for 20. Similarly, I will start 20 with 10. I'll find it's greater than, come here. So it's greater than 15 even. So I can connect 20 in this side. Then for 18, you see 18 is greater than 10, right side. 18 is greater than 15. Again, there is a right subtree of 15. So you cannot connect 18 over here. Come here. 18 with 20. 18 is lesser than 20. So that means 18 should be somewhere over here. Similarly, if you go for 5, you see 5 is lesser than 10. So 5 should be the left side tree of 10. So left subtree already contain a root, that is 3. So that's why you come to left first. I will get 3. 5 with 3. We can see that 5 is basically greater than 3. So 5 should be the right subtree of 3. and right subtree of 3 is blank. So I can now connect 5 over here, and then I will get 1. Similarly, 1 is lesser than 10, and I will come in the left side of 3, left side, I will get 3. 1 with 3 means 1 is lesser than 3. That means in the left side of 3 I should connect, and it's blank. So you can easily connect 1 over here. And then I will get 6. 6 is again greater than 5, right? I mean, greater than 5 I am directly saying, because ultimately if you start journey from 10, you will become 6 is lesser than 10, you will come in this side. 6 is now greater than 3, you will come right side. Now 6 is greater than 5, and greater than 5 right side is blank. So you can connect 6 over here. And then 14. Now what the 14 will come? You see 14 is greater than 10, 14 is lesser than 15, 14 is greater than 12. So let's connect 14 over here. So you see, that means, you see, if without considering the whole tree as a binary, actual binary search tree, this is the left subtree with considering 10 as a root, and this is the right subtree considering 10 as a root. So you see the relationship that left is lesser than parent, and right is greater than parent. The whole left subtree is actually lesser than parent. So left does not mean that only the left node. It means that if we have a node A and we have a left subtree over here where I have n number of node, and we have a right subtree here also, some right subtree. I'm not interested about their depth, and there is m number of nodes. So every n number of node, I mean all the n nodes are less than a, and all the m nodes are greater than a. So this is true not only with respect to considering if I consider for root. You see, if you consider this 3 as the root of the, if you consider only the left subtree, in the left subtree, this part is the left subtree of this particular node 3. Considering this is as a you can say root, and this is the right subtree considering this 3 as a root. So you see, here also left subtree is lesser than no parent, and right subtree is greater than parent. So basically this left subtree is, this particular condition is true recursively for each and every non-leaf nodes of the tree. Anyway, so ultimately the tree that we have formed is something like this. So now let's move on. Let's move on for BST traversal. So we will now do BST traversal. As already we have seen that there are 3 types of traversal. So that means if a tree is given to you, and if someone do a pre-order and some another person do a in-order traversal, if there is no restriction, both are correct. Okay, so you cannot consider that this one is actually the correct one and other ones are actually false. No, any order is correct. Any of these 3 order is correct. Okay, so now let's try to realize the order with respect to a very simple tree considering the nodes not with respect to a value, with respect to some variables, then we will consider what will happen with respect to this particular value. So let's do it. Suppose we have a tree, we have a binary search tree, something like this: A, B, C, suppose D, sorry, D, E. I'm trying to make it little bit complicated so that we can actually capture various situations that can be possible over here. For example, we have a right, and then say we have both left and right of this one, and then maybe this one is true. I mean, G R A G H in this side, suppose. Okay, so suppose this is the situation. So this is the, suppose a binary search tree. Okay, and I ask you to for the traversal. So the first one that we will do, that is preorder. And we know that preorder means node, then left, then right. So you see, it's very trivial that we will start with this root. This is my root, and we will start from here. We are standing over here because we don't have any address of any other nodes. Because these nodes are also created dynamically, as we have seen in case of linked list. That means we don't have any idea about the existence of this node unless we have a key to reach to node A. So we are standing over here, that's true. Now if you apply preorder with respect to these nodes, so that means consider only the nodes up to this. If you consider this is your tree, forget about the other part, then you will say that okay, so it will become in order means basically A, B, C. Yes, you are correct. But problem is that this B is not a leaf node. B also have some child. So with respect to this B as a root, this is another set of three nodes having parent-child, similar parent-child relationship. So with respect to this B, D and E, it should be B, then D, then E. So that means this B is not true only. After B, you cannot put this C because this B represents the whole thing. So that means we have to, once we reach to a particular node, we have to consider that node as the parent or the root, and their left or right child as their child, and you have to apply the similar preorder technique for that case only, and then only we can proceed. So if we just erase these boundaries, I hope now you will be able to realize what actually we are going to do. So that means these things will not be there. So if we do this now traversal, we will obviously we will start with this A because it is my root. Fine. And then we will have B. This B is possible because with respect to B, D and E, these three nodes, this is the parent, that is the node. So with respect to preorder, node should be printed first. So that's why with respect to this 3, B should be printed first. So I can print this B. But then I cannot print C because I have to go to till downwards. And we will see that we have a left subtree of B. That means till we don't have any left subtree, we will proceed. And we will stop when that's the leaf node. And then we will start returning back and we will go to the right side of its parent. So after printing B, I came here. I will see that I have only one. I mean only one node, that is root. I mean this left subtree contain only one node. That means this node contain no child. So for something like, if I assume that you have a node X which don't have any child, so basically it's pointing to null and it's also pointing to null. And what will be the preorder for this particular case? You can say that X, then null, then again null, right? But null and null, basically null doesn't mean any existence. Null means there is nothing. So that means you can omit this whole part and only X is there. So similarly, after printing B, if you go left and you will see D, then left null and right also null. So that means we will have only D. So it's my node, it's my left, then I will come right. So node left, right. So first A was node, I came here, it's my left. So I printed this. And now I am considering this is my node and I came in left and I have printed this. And I don't have anything in the left side. Even I don't have anything in the right side. That is why now I can go back to B again, but I will not print again because I have already printed with respect to the pre-order technique. Then we will go to the right and we will print this E because node left and right. Now when I came here, I am standing on this E. This is my node right now, currently, where I am pointing. If this is node, this H is left child and right child is null. Now with respect to this three, that E, H and null, obviously should be printed first because node is printed first. So after D, we will print E. Then we will print H. After E, in the left side we will print H. And there is nothing. I mean, if we can say that we have a null. But you don't need to say right, comma null, because null means there is nothing. You can omit this. And you see, since there is null, nothing in the right side of E, that means the whole right subtree of B is completed. If the whole right subtree of B is completed, that means whole tree is completed. If this whole tree is completed, that means you see, if you have printed node with respect to the original tree, if you have printed node, then this is your entire left of the actual tree. I'm saying with respect to actual tree. And now we have to go for right. So now I can go towards right. I'll return back to my root again. I'll go towards right and I will get C. Yes, C should be printed first because when I will jump to the right, and now this C become my node, which is the root, basically representing present root. So presently if C is root, then obviously C can be considered as the node and I can print C. And then C don't have any left child. So after comma, after C, I can easily write null, but there is no meaning of writing null again. You can remove this, even you can remove this null also from here. So it's better to remove so that you will not get confused in some situation. So anyway, so after H, that means ultimately we will have C, and then we don't have any left child, so forget about left child of C. That means I'll go towards right and I will print F first, because when I will go towards right, this become my newly, temporary true root of the of the tree having root F. So my tree is now F, G and I only, right? Forget about the other part. So after C, that means I will print F, and then we can print its left child, which is basically G, and then its right child, that is basically I. And you see, this I is completed means the whole tree is completed. If this right subtree of this C is completed, that means whole tree with respect to C as a true is as a root is completed. If the whole right subtree is completed, that means basically with respect to the original tree, you have completed the right subtree. So this was your node, this was your left subtree, and this was your right subtree with respect to original tree, and that's why you have completed. So this is a way we can do the pre-order traversal.